We are passengers on a controlled and purposeful explosion. As if we are microbes riding on a piece of shrapnel from an exploding grenade. All of the universe's matter and energy, even space and time, came into existence in a single moment. But far from a chaotic explosion, this initial blast seems to have been finely tuned, as if it has been designed to benefit us and our tiny planet. Today, our knowledge of the heavens and the earth and the forces influencing them is greater than that of all previous generations combined, and our sense of wonder grows with each new revelation. Astronomer Hugh Ross will be our guide as we tour the universe. We'll travel outward in space and backward in time. We'll marvel at the power and the intricate design around us. And we'll gain a clearer picture of our cosmic context, our place in the physical universe, and in the spiritual realm that encompasses it.
Ever since I was a young child, I wanted to know more about the stars and galaxies, to see them up close and unlock their mysteries. Strangely enough, starlight and galaxy light are our greatest tools for unlocking the mysteries of creation. This is the Keck Observatory, the world's largest optical telescopes. Together, these two telescopes have 8 times the collecting area of the Mount Palomar telescope and more than 30 times that of the Hubble Space Telescope. The Keck telescope has 36 independently driven mirrors. Computers control the movement of these mirrors so that they work in sync as one gigantic 400-inch telescope. It's also very precisely figured down to a molecule's thickness. With sensitive light and radio wave gathering instruments like this, we can look out billions of light years into space to the very limits of the cosmos itself. But as we look out into space, we're also looking back in time. This is where astronomy is unique among the sciences, because it alone directly observes the past.
As a matter of fact, astronomers are always observing the past. Light waves, radio waves, and all other kinds of electromagnetic waves may seem to reach us instantaneously, but they don't. They seem to because they travel so fast. Light speeds through space at 186,000 miles per second, fast enough to circle the globe 7.5 times in a second. When we look at the sun 93 million miles away, we're seeing what it looked like when the light left it about 8 minutes ago. Likewise, when we look at the moon, we're seeing it as it appeared about 2 seconds ago. When we look out to the stars, we're seeing them as they were thousands, millions, even billions of years ago. The farther away an object is, the longer ago its light began its trip through space. The distance light covers in a year, about 6 trillion miles, we call a light year. Light years offer a more convenient method for indicating vast distances. The most distant galaxies ever detected by astronomers are about 13 billion light years away. That means the light from those galaxies took 13 billion years to arrive on Earth. As we gaze at this galaxy, we're looking back in time at how it appeared 13 billion years ago.
The distance back to the dawn of the cosmos is finite but enormous. So let's scale it down to a manageable or imaginable distance we can more easily understand. Let's compare it to the distance between the Space Needle here in Seattle and the Empire State Building in New York City, about 2,500 miles. The Space Needle can represent our current position in time, and the Empire State Building the beginning of time.
As we travel out into space and back in time, we'll check our progress on this landmark-to-landmark cross-country map. Our time machine will be a telescope. We will peer back in time, all the way back to the moments just after the creation event, almost 14 billion years ago. And as we travel back in time, we'll do some sightseeing along the way and explore this question. Is the Earth a common rocky planet, possibly one among many, maybe even thousands of life support sites? Or is it one of a kind, uniquely fit for humans?
Now we're ready to start our journey back in time. We'll begin with our nearest neighbor in space, a cosmic hitchhiker only 2 seconds away, the Moon.
Our Moon has long mystified astronomers. It is so large relative to Earth that the Earth and Moon together are often classified as a double planet system. But studies of gravity show that no such double planet can form out of a single gas and dust cloud so close to a star as we are to the Sun. The Moon must have formed later through some unusual process. Moon exploration enabled us to confirm that lunar rocks differ chemically from Earth rocks. Through study of lunar rocks' radioactive decay, researchers discovered that the Moon is in fact nearly 100 million years younger than the Earth. In the 1990s, a theory explaining the Moon's existence gained wide acceptance in the scientific community. According to this theory, an object the size of Mars crashed into the newly forming Earth about 4.5 billion years ago. Most of the object's mass was absorbed by the Earth, but this collision also sent up a huge cloud of dust and rocky fragments all around the Earth. In time, gravity pulled those fragments together into one solid body, the Moon. The Earth, meanwhile, lost its entire atmosphere, and a new, much thinner one began to form from gases released by Earth's crustal material. Such a collision may seem a disaster, but it proved just the opposite. It set in motion certain alterations to Earth's features that eventually made this planet a uniquely suitable site for life.
The odds against a collision benefiting the eventual support of human life are staggering. The planet colliding with the Earth would need to be the right size, moving at the right velocity, striking at the right angle, made of the right materials, and occurring at the right time in the development of planet Earth. If any one of these factors were off by just a few percent, the Earth would be barren today.
Unless that impact had occurred, Earth's atmosphere would be much heavier than it is, even heavier than that of our neighboring planet, Venus. Venus's thick carbon dioxide-filled atmosphere would mean instant death for all possible life. The extra mass Earth gained from the collision, along with its atmospheric revision, meant that water could exist on Earth in all three states: ice, liquid, and vapor, and in huge supply, a supply absolutely essential for an efficient, consistent water cycle. and that water cycle is essential for life, both for its existence and survivability. Besides the Moon and an occasional asteroid, Earth's nearest neighbors are the planets Mercury and Venus on the inside, between the Sun and the Earth, and Mars on the outside. Our closest neighbor, Venus, like Mercury, is so close to the Sun that the Sun's gravity has worked like a set of brakes on its rotation period. Venus takes 244 Earth days to spin around just once. Our planet rotates about 4 times more slowly today than when life first appeared. Scientists have determined that a more radical change in Earth's rotation rate would have been catastrophic for life. Mercury, like the Moon, has only a slight atmosphere. Therefore, since virtually no erosion has occurred, Mercury's oldest geologic features remain, the scars of ancient impacts by asteroids and comets. Mercury's meteor-scarred landscape documents for us the early history of the inner planets, a time of intense asteroidal and cometary bombardment. This heavy assault not only took place on Mercury, but also on Venus, Mars, and the Moon. Likewise, the primordial Earth was not spared from this intense bombardment, even more so because of Earth's greater mass. This heavy bombardment resulted in searingly hot conditions, hot enough to vaporize the Earth's oceans and melt the Earth's crust. Obviously, no possibility for life existed at that time. For decades, scientists theorize that life on Earth arose from a vast collection of non-living molecules called the prebiotic soup, a process that required billions of years. But now research has shown that life arose quickly, in less than a few million years after the late heavy bombardment. In addition, there is no evidence for a prebiotic soup. If there was a prebiotic soup, we would expect to find the remains of it in ancient carbonaceous material, such as kerogen and graphite. As it turns out, all carbonaceous material on and in the Earth comes from postbiotic material, the decay of established life. Given so little time and the absence of a prebiotic soup, some scientists now look to the heavens for answers to the origin of life problem. They look up, not for a supernatural cause, but to search for other sources which could have deposited the seeds of life on the early Earth. Could life have arisen on one of our planetary neighbors and then have been transported to Earth? Many scientists are now looking to other planets to find support for this idea. But even if we were to find life on a nearby planet, where did that life come from? How can we be sure of any life we find on a nearby planet is not really the cross-contamination from the abundance of life on Earth? The Earth is brimming over with life. It's only a matter of time before we find the remains of these Earth organisms on Mars. And many scientists will claim this is undeniable proof that life arose by natural processes there. But a simple test exists which would prove these organisms came from Earth.
All DNA has a consistent complex signature or order to its structure. This signature is passed down from each living organism before it. If the DNA signatures found in the remains of life on Mars match that of the DNA found in life forms on Earth, then the only logical conclusion is that the stuff on Mars must have somehow come from Earth.
Just as asteroids and comets colliding with Mars can send Martian rocks to Earth, so too collision events on Earth send Earth rocks to Mars and the rest of the solar system. While Mars is the best candidate beyond Earth for finding the remains of Earth life, it offers a far from hospitable environment. Mars is so dry, its atmosphere so thin, and its gravity so weak that a drop of water evaporates in less than 1 second on the Martian surface. Radiation, violent storms, instabilities of axis and orbit, and freezing temperatures lower than the Antarctic winter mean life cannot survive there, at least not for long. Billions of years ago, Mars had a warmer and wetter climate, which led scientists to speculate it could have spawned life. However, the chemical environment of early Mars was even harsher than Earth's, making a naturalistic scenario for the origin of life impossible. The next stop on our flight is the giant planet Jupiter, 10 times farther away from us than Mars. At a distance of 400 million miles from Earth, we have traveled less than a millionth of an inch on our journey from the Space Needle to the Empire State Building. Jupiter is 40 light minutes away from Earth. That means it takes light from Jupiter 40 minutes to reach the Earth. Jupiter is such a colossus that it outweighs by 2.5 times all the other planets in our solar system combined. The giant red spot we see as we look at the top of Jupiter's dense atmospheric layers shows a 2,000 mile-per-hour hurricane raging for centuries. To give some perspective, that spot is 4 Earth diameters across. Of Jupiter's several dozen moons, Io, Europa, and Ganymede are the 3 most closely studied. Each of them is larger than our moon and less tranquil. Io sometimes suffers violent volcanic eruptions. Some astronomers believe Europa may have subterranean liquid water, and that this water spawned life. Given the importance of water, it's no surprise that scientists have named Europa as a candidate for life. But recent studies of the craters on Europa's surface have established that its ice sheet is at least 12 miles thick. Such thick ice prevents any oxidants from reaching whatever subterranean ocean may exist. Without oxidants, no metabolism. Without metabolism, no life is possible in Europa. Moreover, as we shall continue to see, water is but one of more than 200 physical characteristics that must be met for life to survive, let alone what it takes to generate life. Researchers in the 1990s sought to probe Jupiter's many mysteries, such as the degree to which light penetrates those thick clouds, and whether the planet has a rocky core or just super dense frozen gases. In the course of their investigation, they discovered evidence of Jupiter's importance to Earth life. Jupiter is positioned and dimensioned to shield Earth from collisions. The planet's nearness and mass typically deflect comets and asteroids that are moving on a collision course with Earth. Occasionally, Jupiter itself takes the hit, as in this 1994 encounter with Comet Shoemaker-Levy. Though each fragment of Shoemaker-Levy was smaller than Manhattan Island, 21 of them raised fireballs more than 10,000 miles high and made Earth-sized bruises in Jupiter's atmosphere. Any planet capable of sustaining life needs a just right-sized Jupiter standing guard to shield it from life-ending asteroid and comet impacts. Jupiter's size and position are important to Earth life for yet another reason. If Jupiter were any larger than it is, or any closer to Earth, its gravity would wreak deadly havoc on Earth's orbit. Jupiter is a just right size protector in a just right location. Traveling another 40 light minutes out from Earth, we arrive at another giant planet, Saturn. Saturn has about a third of Jupiter's mass, and it still outweighs all the planets other than Jupiter by several times. 1,000 Earths would fit inside Saturn's volume. Titan is Saturn's largest moon, and has gained notoriety as another possible candidate for prebiotic chemistry. Titan is the only solar system body besides Earth with a significant atmosphere, one which contains high levels of nitrogen gas. Unfortunately, Titan has no ammonia and only trace amounts of water and other oxygen compounds. Without these critical ingredients, none of the building blocks of life molecules can be chemically assembled. The next two planets we encounter are also gas giants, Uranus and Neptune. Uranus is 15 times more massive than Earth. Like all planets this large, including Jupiter and Saturn, it's mostly gas. Uranus, like Saturn, is surrounded by concentric rings, but unlike any other planet in the solar system, its rotation axis points toward the Sun. Neptune, just slightly larger than Uranus, features a great dark spot, presumably a large, stable hurricane like Jupiter's Great Red Spot. Neptune's largest moon, Triton, orbits in the opposite direction to the planet's rotation, leading us to conclude that it was captured after Neptune's formation. Neptune is more than 4 light hours away from Earth. From Neptune's surface, the Sun would appear as just a bright point in the sky. Neptune is so frigid that ammonia and nitrogen would liquefy there and gasoline would freeze. These 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, travel in unique, almost circular orbits on a horizontal plane around the Sun. This stands in stark contrast to gas giants so far discovered outside our solar system, which either orbit too close to their stars or have elliptical and/or non-horizontal orbits. Even a slight deviation from their appointed paths would be catastrophic for life on Earth. Traveling out almost 6 light hours from Earth, we come to Pluto and its companion Charon. Pluto is the smallest planet in our solar system, smaller than our moon, made mostly of ice. Pluto's moon Charon is less than half Pluto's size. Beyond these frozen outposts lie other tiny bodies orbiting the Sun. Now we reach the last stop before departing our solar system, a vast area of asteroids and comets. The inner ring is called the Kuiper Belt. The density and positions of these asteroids act as a stabilizing force for the orbit of Neptune. Without a finely tuned gravitational tug from these space rocks, Neptune's orbit would be erratic, potentially catastrophic for our tiny planet. At the outer edge of our solar system, orbiting the Sun up to 2 light-years away, lies a vast area of over 100 billion comets known as the Oort cloud. Occasionally, some of these comets are disturbed just enough by the gas giant planets to be pulled out of their orbit and hurtled toward the inner solar system, including the Earth, replenishing our water supply and delivering other vital nutrients. On our trip across the United States, we have traveled just 0.04 of an inch from the base of the Space Needle toward the Empire State Building. As we leave our solar system, we travel more than 4 light-years to Alpha Centauri, the nearest star to our solar system. Only about half of the stars in the entire universe are classified as single or bachelor stars like our Sun. Alpha Centauri is not a bachelor star. It is one of the common multiple star systems. The gravitational tug-of-war in Alpha Centauri makes stable orbits for planets capable of supporting life impossible, so the majority of stars are ruled out as possible life support sites. As we continue on our way, we discover that stars come in different sizes, colors, and ages. The bigger the star, the hotter, faster, and more erratically it burns up its fuel. Stars more massive than the Sun burn their fuel too quickly and erratically to support life in their vicinity. Stars less massive than the Sun are cooler, so planets orbiting close enough to be warm enough for life would have their rotation greatly slowed by the star's gravitational tug. Slow rotation means long days and nights and life-destructive temperature extremes from day to night. Traveling 250 light-years out past Alpha Centauri, we encounter over 100,000 stars. Of these stars, only 100 of them so far have been found to have planets orbiting them. Scientists now estimate that only 2% of the stars in our galaxy possess planets. Most of the planets discovered so far are gas giants, several times more massive than Jupiter. All of them either orbit their star closely or have non-circular, non-horizontal orbits. Either way, they would destabilize any small rocky planets like Earth that might be near them. One candidate for a planetary system which bears some resemblance to our own surrounds a star named 55 Cancri in the constellation Cancer. At a distance of 41 light-years from Earth, this star is about 5 billion years old, just about the same size and age as our own Sun. This planetary system contains 3 gas giants, similar to those found in our solar system. But the similarities end here. While one of the gas giants orbits 55 Cancri at roughly the same distance as Jupiter orbits the Sun, it is 4.5 times more massive than Jupiter. This extra mass would disturb the orbit of any Earth-sized planets that might exist there. As for the other 2 gas giants, both orbit 55 Cancri so closely as to guarantee a deadly tug-of-war with any possible life support planet. So far, none of the extrasolar planets cataloged by astronomers possesses even one of the more than 200 design characteristics necessary for life. Chances are we'll find thousands of planets outside our solar system, but the possibility that we'll find a whole suite of planets, like those in our solar system, uniquely positioned to sustain life on one planet is growing more remote every day. Further out from Alpha Centauri, but still within our Milky Way galaxy, we also encounter hundreds of gas and dust clouds called nebulae. Their strikingly beautiful colors are created as the nebulae are ionized. Radiation from nearby large stars supercharges the electrons and sends them flying away from their atoms and molecules. As electrons escape from hydrogen atoms, they produce a red glow. As they leave oxygen atoms, they produce a blue-green glow. Gaseous nebulae may be described as stellar maternity wards. Our galaxy, called the Milky Way, is still giving birth to new stars. Our own sun is considered a late-born star, and as you'll see, life depends on that critical timing. Stars form within nebulae much the same way raindrops form within Earth's clouds. Gravity is a key factor. Gas and dust particles begin to pull together under gravity's influence. But as they do, more molecules collide, producing heat. As the particles continue coalescing, more and more heat results, especially at the core of that condensation. Eventually, the core becomes hot enough to ignite nuclear burning. At this ignition point, a new star is born. Since our sun also went through this type of birth process, most scientists classified it as an ordinary star. But several recent discoveries have caused astronomers to reconsider this assumption. Evidently, our sun is very rare indeed. Most stars are either too small or too big, too young or too old, contain too many metals or not enough metals. Our sun's radiation and its precise location in our galaxy are all critical factors for life. A few tens of thousands of light years beyond the center of our Milky Way, we arrive at the halo, where most of the oldest stars reside. This earlier generation of stars is important in the construction of life-essential elements. These ancient stars, in one sense, are the forebears to our planet and to our own existence. As stars exhaust their fuel and die, they bequeath to us their ashes, the heavy elements needed for the next generation of stars and for planet building. Our Earth could not even exist without 9 billion years worth of ashes from dead and dying stars. Stars about the size of our sun, or smaller, lose their outer layers gradually. When the last of their nuclear fuel supply is exhausted, all that remains is a burnt-out core like a cinder after a fire. These cinders, called white dwarfs, take over 10 billion years to cool and play a critical role in our existence. For only on the surface of a special white dwarf binary star is the life-essential element fluorine manufactured. Without fluorine, certain proteins would be unable to form, and life in the universe would be impossible. Even more remarkable is the fact that even with as many as 1 trillion galaxies in the universe, our galaxy, the Milky Way, is likely one of only a few where sufficient fluorine production sites exist. When a star larger than our sun runs out of fuel, the outer gas shells undergo a sudden collapse. They crash into the core with enough momentum to ignite one final eruption, an explosion so intense that when it happens in our own galaxy, it's bright enough to be seen during daylight hours. This final cataclysmic blast, a supernova, produces many elements essential for life: carbon, nitrogen, oxygen, phosphorus, potassium, sulfur, iron, copper, silver, and many others. It scatters them throughout the interstellar neighborhood to be absorbed later by star-producing gas and dust clouds. All of these various types of stars, in all of their various stages of life and death, play a vital role in our well-being. And far from being a waste, every minute of the past 14 billion years of star formation was necessary in order to enrich our planet with the elements that make life possible. Earth has been hung in precisely the right location to receive all the elements that are essential for life, even though the stars in our galaxy are as numerous as the grains of sand on this beach, namely about 100 billion. Many astronomers are now convinced that it's extremely unlikely that there could be another habitable planet anywhere among them. Even if the just right planetary system were to form from the just right elements of dead stars, there is another critical factor to consider. The life support planet must be positioned at the just right location within the galaxy. Near the center of our galaxy, conditions are too congested. With billions of stars in a relatively small volume, gravitational tug-of-wars make the survival of life-supportable planets impossible, and the radiation there is intense, far too intense for life. Toward the outer edges of our galaxy, the stellar population becomes too sparse for planet building. The heavy elements generated by supernovae and white dwarf binaries are too few and far between, not enough building material to make planets. At almost any distance from our galactic center, conditions within the spiral arms prevent planet formation. Amazingly, our particular solar system resides at the perfect location in between spiral arms, neither too close to the center nor too close to the outer edge. Our just right location not only permits our existence, but it also allows us to see and explore our region of space. No wall of high-rises, no big dust clouds block our view. On our travel map across the ages, we reached the center of the Milky Way here at 25 feet from the Space Needle's base. Going past the center towards the halo, we had another few feet. When we are ready to exit our galaxy and move out into the vast reaches of space, we'll have come only a little more than 50 feet on our scale map. Our first stop beyond the Milky Way is the Andromeda Galaxy, slightly more than 2 million light-years from Earth. That means we're looking at Andromeda as it appeared a little more than 2 million years ago. Andromeda resembles the Milky Way in structure, but it's about twice as big. Together, our galaxy and Andromeda account for nearly 7/8 the total mass of the small galaxy cluster in which we reside, a cluster colorfully named the Local Group. The vast majority of galaxies reside in dense clusters, and these clusters must be ruled out as possible life sites. The gravitational tug-of-wars among these tightly packed galaxies render them unfit for life. Fortunately, our local group is not a dense cluster. Also, it is located in the extreme outskirts of another cluster, the Virgo cluster, safe from the gravitational wars. On our way to the Virgo cluster, we pass by several beautiful galaxies. In the South Polar Group, about 8 million light-years away, we meet with NGC 300, with its lengthy spiral arms. We can see them extending all the way out from the nucleus. Only 6% of the galaxies in the universe are spirals like our own, and only spiral galaxies can contain planets in stable orbits about their stars. This one design characteristic alone significantly restricts the number of potential sites for life. Just slightly farther along, we see NGC 253, a spiral seen edge-on. The nucleus is unusually small with no central bulge visible. M81, about 11 million light-years away, has a huge central bulge and rather thin, regular spiral arms. Even the size of a galaxy's bulge must be fine-tuned in order to sustain life. If the bulge is too large, then a planet like Earth will be blasted by deadly radiation. If the bulge is too small, then not enough planet-making gas and dust gets funneled to the zone in the galaxy where life support planets would need to reside. M81's neighbor, M82, is another spiral, but we see it edge-on. An enormous eruption of gas and dust is exploding out from M82's nucleus, perhaps ignited by a burst of star formation. Centaurus A, 15 million light-years distant, is highly irregular in that it has a thick dust lane perpendicular to the major axis of the starlight. More typical is a sombrero galaxy, where the axis of the dust and the axis of the starlight coincide. The location and quantity of dust in a galaxy is critical for determining whether or not any life-supportable planets can form. Just past 30 million light-years away, we find the Whirlpool Galaxy, actually an open spiral galaxy interacting with a smaller, irregular galaxy. The center of the Virgo cluster is 45 million light-years away. Here sits M87, an elliptical galaxy, one of the more common types of galaxies in the universe. Because of its shape and lack of spiral arms, it cannot give rise to life support planets. M87 is 10 times more massive than the Milky Way, and one of its distinguishing features is the black hole at its core. This hole weighs in at 2 million solar masses. 75 million light-years distant, we reach the Fornax cluster. It contains this beautiful spiral galaxy, NGC 1365. Some astronomers believe the bar may be a temporary feature caused by infalling gas. We see a burst of star formation along that bar. With galaxies packed so close together in clusters, collisions are inevitable. Here, two spiral galaxies are in the throes of a head-on crash. The next cluster we meet in our journey, the Hercules cluster, is over 400 million light-years away.
Just from this cursory view of our galactic neighbors, we observe that a staggering number of factors must come together to sustain life. We need a just right planet with a just right sun, placed in the just right location of a just right spiral galaxy with a just right mass and the just right size bulge. That even one planet in a galaxy could contain all of these features seems nothing less than miraculous. By now, we have traveled 67 miles from the Space Needle on our way back to the Empire State Building. Once we've reached this point, at 400 million light-years from Earth, beyond the Hercules cluster, we come to a cosmological desert where the scenery virtually disappears, not because there's nothing there, but because we cannot see clearly enough through our windows. Until recently, we had very few measurements and images of this region of the cosmos. Thanks to many new instruments, like the Keck telescopes, the Hubble Space Telescope, the COBE satellite, and others, the curtains are beginning to draw back. Even so, information is still limited. Only a few dozen images are available. For our journey, this segment of space is shrouded in haze. But here and there, our telescopes pierce through to capture images of distant quasars and galaxies.
Millions of galaxy clusters fill the universe, each containing thousands of galaxies, adding up to 10 billion trillion stars. That's 10 with 21 zeros after it. To try to get a handle on this colossal number, consider this. If 10 billion trillion dimes were stacked on top of each other, the line of dimes would make 125 trips to Alpha Centauri and back. As vast and innumerable as all these galaxies and stars may seem, and as tiny and insignificant as they make us feel, this enormity is essential to life's existence.
In order for the universe to sustain even one life support planet, each one of these 10 billion trillion stars is a necessity. If the number of stars in the observable universe were any greater or any fewer, life would be impossible.
If there were fewer stars in the observable cosmos, nuclear fusion would be so inefficient that the only elements to form would be hydrogen and helium. With more stars in the universe, all the elements would be heavier than iron. No carbon, no nitrogen, no oxygen. Only in a cosmos with a finely tuned mass of ours can the life-essential elements be produced. So as it turns out, the vast reaches of the cosmos are not a big waste of space, energy, matter, and time. When we travel to about 6 or 7 billion light years away from Earth, we are confronted with a remarkable discovery. In April 2000, scientists published the results of a landmark study in which they used a balloon-mounted telescope over the cold, stable atmosphere of Antarctica to test several characteristics of the universe. Known as the Boomerang Project, the cold, stable atmosphere of the South Pole enabled scientists to more precisely calculate the universe's rate of expansion. Apparently, for the first 8 billion years after the creation event, the expansion of the universe was slowing down, like shrapnel after an explosion. But the boomerang experiments revealed that for the last 6 billion years, the expansion of the universe has been speeding up. Scientists discovered that there are two factors precisely governing the expansion of the cosmos throughout its history: mass density and space energy density. The mass density, which dominated the first half of the universe's existence, slows down cosmic expansion, while the space energy density, which dominates the more recent half of cosmic history, speeds it up. This delicate balance represents the greatest fine-tuning ever discovered. If the mass density were to vary by more than 1 part in 10 to the 60th, or the space energy density varied more than 1 part in 10 to the 120th, life would be impossible anywhere, anytime in the universe. As we move farther and farther away, farther and farther back in time, we begin to see some mysterious objects called quasars. Only since the mid-1960s have we built instruments capable of detecting them. Since that time, we have learned that when very large galaxies are young, intensely powerful plasma reactors form in their nuclei. These reactors burn with such intensity during this stage, called the quasar stage, a tiny core in the nucleus, a core no bigger than our solar system, outshines the rest of the galaxy by many orders of magnitude. Ordinary galaxies, far back in their formative stages, burn so dimly that only telescopes as powerful as the Hubble Space Telescope and the Keck can successfully image them. The galaxies shown here are so distant that the light picked up by our telescopes was emitted about 5 billion years ago. These galaxies are 10 billion light-years away. They allow us to glimpse what the universe looked like at a third of its current age. Take a deep breath. Imagine how you might have felt at age 15 seeing a baby photo of yourself for the first time. This image from the Hubble Space Telescope carries us farther back in time than any optical telescope has ever gone. We're looking at the cosmos just 500 million years after the creation event. No galaxies yet, only the building blocks of galaxies, pockets of condensed gas in the process of forming huge clusters of stars. If we want to get close back to the moment of creation, we need to turn up the power in our time machine. We'll need a new mode of transportation to carry us the rest of the way back to the Empire State Building. Our new vehicles will be radio and far-infrared telescopes. With these instruments, we can look back to the time before galaxies. If our eyes could see radio waves or infrared waves, we would be able to see distant galaxies more easily. But our eyes can only see electromagnetic emissions in the visible light wave spectrum. Waves in the radio part of the spectrum allow us to peer back in time even farther. This map of the cosmic background radiation, literally the radiation left over from the creation of the universe, carries our eyes as far back in time as any telescope can possibly take them. Here we are just 380,000 years away from the actual moment of creation. On our trip from the Space Needle to the Empire State Building, we have now arrived within 250 feet of our destination. We cannot look back any farther because 380,000 years after the creation event, light first separated from darkness. The view before that time would only offer a featureless glow. We can't see beyond this glow because previous to 380,000 years after the creation event, the universe was too hot for atoms to exist. Electrons could not orbit around nuclei. Because the universe was nothing but charged particles, an amorphous glow is all that appears. For an earlier look, we need to use entirely different vehicles, entirely different instruments, particle accelerators, supercomputers, and gravity wave detectors, not telescopes. With these machines, we can duplicate many of the physical conditions of the cosmos at its earliest moments. The study of the cosmos can be compared with the backward running of a fireworks video. As we measure and observe the cosmos closer and closer to the first moment of its existence, we are running the tape backward toward the moment of creation. As we draw closer still to the creation event, we observe the universe becoming hotter and hotter. Eventually, in this backward replay, the universe will be so hot that protons and neutrons can't stick together. All atomic nuclei fall apart. At this point, we're just 3 minutes away from the creation event, less than 1/10 of a millionth of an inch from the Empire State Building, just a few molecules away from its base. Let's push on. As we probe even earlier, we encounter a blinding flash, just 1 millisecond from the creation event. This flash is generated by the sudden annihilation of all antimatter in the universe. A delicate balance of 1,000,000,001 particles to every billion antiparticles guarantees the existence of matter in the later universe, and it also guarantees the possibility of life. Pushing back to just a few dozen microseconds from the creation event, protons, neutrons, antiprotons, antineutrons decompose into even more fundamental particles called quarks. At 1/10,000,000,000th of a second from the creation event, the universe is too hot and too dense even for quarks to exist. At 100 billionth of a trillionth of a second from creation, the universe is too compressed for light to be possible. The universe is now completely dark and smaller than a single atom. All we see at this proximity to the creation event are the shrinking dimensions of length, width, height, and time. That is, until we reach a speck of time, just a 10 millionth of a trillionth of a trillionth of a trillionth of a second from creation. Before this moment, all 10 dimensions of the universe began to expand. After this instant, only 4 dimensions continue to expand. So what has happened to the other 6 spatial dimensions? They remain tightly curled up, smaller than 1/1000,000,000th of a trillionth of a trillionth of an inch, around our dimensions of length, width, height, and time. These other 6 dimensions still exist, but with no possibility of uncurling. Let's dare to roll back the film the rest of the way. The universe continues to shrink, the 10 dimensions growing smaller and smaller. At the creation threshold itself, often referred to as the Big Bang, all 10 dimensions become infinitely or near infinitely small and suddenly disappear. And it is from this infinitely small beginning that the entire universe sprang forth, in every aspect, from the formation of planets, galaxies, stars, to the relationship between the mass energy and the space energy density, and even the laws of physics themselves must have been carefully fine-tuned from the creation event in order to make life possible for this brief moment in cosmic history on our tiny blue dot. But some might still argue that the Earth is not really all that special. If we believe the Earth is unique, some might argue that we're in danger of going back to ancient times, when the Greek mathematician Ptolemy popularized the idea that the Earth is at the physical center of the universe. This geocentric view dominated Western thought until the late 16th century, when Copernicus revived an alternative scenario that the planets orbit around the sun. Then Galileo peered through his telescope and rocked the world with observational evidence that Copernicus was right. This Copernican revolution describes a modern mindset that Earth is mediocre, just one tiny planet in a vast cosmic sea, and that the potential for finding many Earth-like planets is out there just waiting for discovery. But the more astronomers learn about the universe, the more evidence they find that the conditions necessary for life are far more numerous and far more narrow than anyone imagined. During our journey back in time, we have explored just a few of the over 200 finely tuned characteristics needed in order for any life to exist on any planet. This idea, known in astronomical circles as the anthropic principle, demonstrates that the universe has been crafted for the benefit of man. Religious, agnostic, and even atheistic astronomers use the anthropic principle as the foundation for their research of our vast cosmos. Increased understanding of the anthropic principle seems to be causing a new kind of revolution in the astronomical community. In one sense, Ptolemy's idea of geocentrism doesn't seem so silly after all. While Earth certainly isn't at the geographic center of the universe, it does seem to be at the biological center. Far from being a common, mediocre, rocky planet, Earth seems exceptional in every way. So what are we to make of all the observations that the entire universe appears to have been meticulously designed for humans? You could just say, what a coincidence, or it's just chance. But most astronomers don't seem to find those answers very satisfying. The fingerprints of intentionality and purpose are unmistakable. And here we confront the cause of the universe, what some astrophysicists call the entity. Listen to what a few prominent scientists have said about the origin of the universe. Physicist Paul Davies has moved from promoting atheism to conceding that the laws of physics seem themselves to be the product of exceedingly ingenious design. He further testifies, "There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming." And astronomer George Greenstein, in his book, The Symbiotic Universe, expressed these thoughts. "As we survey all the evidence, the thought insistently arises that some supernatural agency, or rather agency, must be involved. Is it possible that suddenly, without intending to, we have stumbled upon scientific proof of the existence of a supreme being? Was it God who stepped in and so providentially crafted the cosmos for our benefit? Or consider the words of theoretical physicist Tony Rothman. When confronted with the order and beauty of the universe and the strange coincidences of nature, it's very tempting to take the leap of faith from science into religion." And then there are the words of Arnold Penzias, who shared the Nobel Prize in Physics for the discovery of the cosmic background radiation. "Astronomy leads us to a unique event, a universe which was created out of nothing, one with a very delicate balance needed to provide exactly the conditions required to permit life, and one which has an underlying, one might say, supernatural plan. Finally, as Stephen Hawking concedes, it would be very difficult to explain why the universe should have begun in just this way, except as the act of a God who intended to create beings like us. The entity that brought the universe into existence must be the master of all space, time, matter, and energy. This entity must be powerful enough to create space-time dimensions at will, and to exquisitely fine-tune an untold number of cosmic characteristics. More than 200 have been uncovered so far. the probability of all these known parameters randomly coming together would be 1 chance in 10 to the 215th power. A probability so incredibly tiny that statistically speaking, it's impossible. And this probability is becoming even more remote with every new scientific discovery. Such a high degree of design demonstrates that this entity must be a personal being with an amazing creativity, wisdom, power, care, and love to a degree far beyond human capabilities. He has fine-tuned the Milky Way galaxy, the solar system, and planet Earth so its spiritual life can be fused with physical life in this one small place for one brief span on our timeline. More than an accident, more than a random sequence of events, we are passengers on a controlled and purposeful explosion. Our journey toward creation has provided us with an opportunity to gain a glimpse of the Creator's power and provision. But can we know who the Creator is? If this Creator is revealed through any or all of the world's religions, then it seems reasonable that this revelation would not contradict what He has revealed in the record of nature, science, and the world around us. Whether you are a religious person or not, I invite you to put your worldview to the test. Discover for yourself if it describes His glorious creation in a way that is consistent with what we've observed on our journey toward creation.